now that we've got some ideas for some step procedures that we could do that would get us closer to having sorted data, we need to think about how those different algorithms that we derive from those steps would perform. And of course, part of understanding how they would perform would be doing something like big O analysis on them and thinking of the worst case performance for each of them, and possibly even thinking about the best case or what kind of data they might operate the best on. And as we do that kind of analysis and thinking through, we may also notice some features of each of those algorithms that would be a little helpful to us, that might provide some useful outcome, maybe an intermediate result that we get partway through, or maybe something that will remain true at all times about our data, or different things like that. Let's, for our purposes now, focus on thinking about the performance in terms of big O for each of these steps. And then remember that we have to repeat those steps over and over again. So on our 5 numbers here that we're trying to sort, if we think about the worst case for just 5 numbers, with our procedure of proceeding through the list and swapping pairs that are out of place, one thing that we can do is narrow down to the operation that will happen the most often. And that for all of these will be comparisons. We'll be comparing 5 and 2, and then we'll be comparing something with 1, and we'll be comparing something with 10, and we'll be comparing something with 7, depending on what swaps we might have had to do. So we can see that for 5 items here, we had to do 1, 2, 3, 4 comparisons. And for n items, a list with n numbers in it, we would have to do n minus 1 comparisons. And that's our worst case, where we have to step through the list and do all of those comparisons through there. There may be some tweaks that we can do to shave a few off and to save a few comparisons, but remember that we often focus on the worst case because we want to be prepared for what outcomes our users might face and not set them up to be in a situation where something really bad will delay their ability to use our program, or maybe even make our program completely unusable because it takes so long to run. So remember that n-1 comparisons is just one time through the list for our swapping pairs that are out of place. We may have to do that over and over. And so in your analysis in section A, you may have already thought that through and what the total big O performance will be of an algorithm that uses this as its step and does it over and over and over until the list is sorted. Likewise, selecting the minimum and placing it at the start. Well, when we select our very first minimum, we would have to compare all of the numbers in here again to try to find which is the lowest. So we would take 5 and assume it's our minimum, and then compare it with 2 and now assume 2 is our minimum, then compare it with 1 and assume 1 is our minimum, and onward and onward. So we saw that this one had n-1 comparisons it had to do, and similarly our selecting minimum for the case where we have to select the first minimum will take n-1 comparisons. And again, we may get fewer in later steps, and it'll be up to you to analyze what the total complexity class would be for that based on having to repeat that process of selecting the minimum. Inserting into a partial sorted list gets a little more complicated to think about. The first time that I insert into that partial sorted list, it will have no data in it already. So I won't have to do any comparisons. That first one will be my best case for this. But in the last case, I'll be inserting, for example, 7 into the list that already contains all of the other data, 5, 2, 1, and 10. And so I may have to compare 7 with all of those remaining 4 items that were already inserted to put 7 into its correct place in that partial sorted list. So it still can take n-1 comparisons. For instance, if 1 were the last item inserted into that partial sorted list, it would have to be shifted and compared all the way down. So it's interesting to note that this performance of the worst example for each of these, we know that this comes at least the first time, that the n-1 there is at least the first time through the list there. And then for the other ones, this was the first time. And in the last case, it was the last item that we inserted that might have to do those n-1 comparisons. So it may vary which situations we hit our worst case performance for them, and it may also vary what arrangements of the data give us quicker performance on these. You may have noticed that with swapping pairs, we can quit early on that one. The bubble sort, we can quit early with bubble sort when the data was already sorted. And so these other algorithms may have some performance gains from having sorted data, or data that's reverse sorted, or who knows what the different arrangements may be that benefit you in these different algorithms. And you may also notice some features that come about as you're doing things like selecting the minimum and placing it at the start. Well, think about that. That means that after 3 iterations through selecting the minimum, you have 3 items that are already in their correct final places. And so what features might you be able to use that for? What situations might that be a helpful thing to have? And so as you look at sections B and C of the activity today, think about not just the speed and number of comparisons, but also what other features arise for those different algorithms that you could use to identify them, and that you could use in different scenarios where it might be beneficial to have, say, the first 3 minima from the data that you're sorting, or to quit early, or different things like that. Good luck.